do something like the Baker Campbell's house of formula, right? You have to compute a lot of commutator, but the result is sort of geometrically obvious because you're just here, you just start with the block vector that point in the x direction, and I rotate it along the z axis with this angle, right? So you should, yeah, it's consistent with the 3D rotation picture, like sort of classical picture of an arrow in 3D. And so for example, then I can write something like this, that the Hamiltonian there is the rotated version of this, right? Because the sigma c is invariant under the c rotation. So the recipe to go into the interaction picture is that suppose that I can write the total Hamiltonian as sort of, well, in perturbation theory, the W would be perturbation, right? And the state vector in the interaction picture from this equation, I can see, right, that the time evolution operator in the interaction picture, if I want to get to this state from side zero, the time, the sort of total time evolution operator, if I do it in the Schrodinger picture, would be the plus here. So this is the reason. Okay, so I guess in this problem, I would just choose UR to be that exactly.อันนี้โอเคโอเคนะครับอันนี้โอเคนะครับ All right, now I remember because I was not sure okay, maybe the perturbation, and you will define this unitary that brings you to the interaction picture by exponentiating this guy, which sort of, in this case, is sort of suggests that I would just rotate, UR would just be a rotation according to this Hamiltonian, although that's sort of not the most convenient thing to do here. Is more convenient to just choose UR to be a rotation according to the this frequency instead. So internal frequency plus the detuning. And so if you do that, then from this formula and from that, I can write that that the Hamiltonian interaction picture is this, where H naught here now would just be the part, yeah, so H naught here would be whatever that is exponentiated to UR, to U sub R, right? And then once you calculate this, then you can put in the Schrodinger equation for the interaction picture. Well, oh, sorry, that's the end, right? Because if I can calculate this, then okay, let's just back up a step. Sorry, it's just we have sort of confusing. We are sort of going in the different direction from this one. I just give it to you, and then you can verify it. But here it's sort of motivating how we would arrive. With figure here, and yeah, so from this, okay, let's summarize the logic here. By choosing this UR, you automatically get this product form of the here. You can decompose the usually conclusion in the Schrodinger picture to these two parts, which means that to explicitly write this down, I have to know two of these. UR is already it's basically how we the whatever the initial the rotated frame that we are moving into. So then the rest would be to find UI is.
อันนี้ติดแล้ว
เพราะอะไร
ขามันเบี้ยวแล้วมันไม่ติดกระถาง
ที่ใส่ให้เดียวอุปกรณ์วิทยาลัยโอเคครับอันนี้มันปิดได้ใช่ไหมRight. So one we get from this form, after we define UR, we have to find UI, right? And so UI would just be the product of UR and the total time revolution. And if you know you can calculate that because you can exponentiate this guy into U and then use the Baker-Campbell's half-dove to calculate the product. But that's not, well, that's a lot of things to do. So as just a case here that the easiest way, an easier way would be to calculate, because this UI is the exponentiation of the Hamiltonian in the interaction picture. So you can first find the Hamiltonian in the interaction picture using this, and then exponentiate it. Yeah. We should get exactly the whole like product form here that's defined in this problem. Okay. Is this clear? Also, the question for Chem, because you asked me about. Okay. Okay. You can ask me later. We can talk later. Yeah, but thank you about yeah, solving the mic problem. Okay. Right. Okay. So let's get back to the thing. Mm-hmm. And I think the third homework is due today. Correct? Okay. By the way, the fourth homework is already on the website. It's due the next Thursday, and maybe if I have time, I will try to put out the fifth homework while I'm away, so that you have something to do while I'm away. But yeah, it's not guaranteed. So just to make sure everyone know, I'll be away the last 2 weeks of August. So from 19, yeah, I'll be back in September. Okay. Okay. So right. So to begin talking about quantum eraser, so I should talk about, well, last time we ended with a discussion about interference, right? And the point there is that if so imagine like the double slit scenario, when in quantum mechanics, when you have two alternatives that are not distinguishable or cannot, like that you cannot distinguish them in that experimental setup, then those alternatives will interfere. Mathematically is meaning that the amplitude you would just so the probability when things interfere will be something like this, right? So the typical form of this is that this psi 1 and psi 2 are partial wave functions that come from the two slits. And then you add or subtract amplitude, or you take the absolute square to compute the probability. But if you somehow know that the electron comes out of either slit 1 or slit 2, then the probability that it comes out from slit 1 would just be this, and probably come out from slit 2 would just be this, right? And then the total probability would just be the sum of the absolute square, where all the information about the relative phase is already lost. Okay. Because here I can have relative phase between psi 1 and psi 2, and that's the reason for constructive or destructive interference, right? The destructive interference is especially important because that distinguishes amplitude, probability amplitude from just normal probabilities, right? Because normal probability cannot cancel with each other. And I can phrase this thing in this scenario in terms of a qubit. Well, I guess there are many ways to do it. If for example, I can think of a Mach Zehnder interferometer. And this is where, okay, how do I want to orient it, this guy? So if I have a beam of light coming into beam splitter, so this is beam splitter, this is beam splitter. So it's split into two beams, right? Well, so now what people would have to do here first is to label the two modes, right? And maybe you can label something like if if the beam of light is on this lower plane, well, I guess you can, well, I can write this as like the bottom arm or something, and then this is the top arm. Well, usually you see left and right instead, but since I already yeah, draw the diagram in this way. So here, when the beam in the bottom arm meets the beam splitter, it's if it's a 50-50. So let's say this is 50-50 beam splitter. So it's split the beam equally. It'd be something like this. You might think that if I put the beam in the top, if I input the beam in the top arm, it would also split the beam in the same way, but that would mean that the time evolution is not unitary, right? Because two orthogonal states, and here they are orthogonal because they are microscopically distinguishable, right? So since B and T are orthogonal, when T goes through the beam splitter, it should evolve into state that is orthogonal to this one also. And so you have to put the minus sign somewhere. Just have the relative phase. So well, I guess it's you can. Well, we are not experimentalists. You can ask experimentalists how to do this, but yeah, yeah. Usually, actually the physics that's happened there is that the beam splitter is actually like a mirror, and it has thickness, and it has like a silver plate is that you can find like the behind whatever like any mirrors, and so the thing is that light that reflect from this side and this side will come out with a different phase. Right, and phase here I mean polarization. And so if you can control, for example, the thickness of this glass, then you can manipulate, you can engineer the sign here. But all else being equal, if this is to obey quantum mechanics, it has to be unitary in some way, right? But for example, in general, you can have beam splitter that's not 50-50 too. So distribute the real part, the weight of the amplitude like differently between the two states. And here, if I put a phase shifter here, so this would shift the polarization vector only in the bottom beam. So if I think of this, yeah, I think let's write this. So the point is that you can think of this as a qubit, as a system of qubit, one qubit, right? Because you have two orthogonal states here. And so let me just label the state in the way that we are used to. And maybe I want to shuffle things around just for convenience. For example, if I want this beam splitter to be the Hadamard gate, I would want this to have a minus sign instead, right? So this is the top arm, this is the bottom arm. So we might want this evolution for this example, which would be the Hadamard gate. Yeah, and I guess just to be consistent with, so I want to draw the quantum circuit diagram for this, and maybe just to be consistent with the convention that every input state is in the zero state, I probably put beam in this direction instead. And so I would have something like this. And since the phase here only affect the bottom part, in other words, the one state in our qubit picture, this is equivalent to a z rotation, right? This is rotation along the z-axis with the angle phi. Which just to say that it gives a relative phase phi between the states 0 and 1. So this is phi z or 2. And then the two beam meets at the beam splitter again, and then we measure which path it comes out. So for spin, this is also called Ramsey interferometer. And it's just for spin. Well, I don't know if it has to be 1/2, but let's say for our sake of example, it's spin 1/2. It is formally equivalent with the Mach-Zehnder interferometer, except that well, physically they're different, right? Because here you use light, there you use spin, and actually here we are just writing things in the first quantization picture, So if you write it in like the second quantized picture, then you would have two modes, and then I write something like, oh, this is the state with the photon in the left, in the one of the mode, and then this state with the photon in the right, in the other mode, right? But it's fun to think about it. You can think about it, but we're not doing that here. But then if you do it in spin, this is the way that people can measure this phase. So for example, this might be some, I don't know, naturally occurring Hamiltonian in the lab that you want to measure the phase. So basically the eigenvalues of this Hamiltonian. So what you do is, well, here, since it's a C rotation, the idea is just to input the state that is a superposition of the eigenstates, right? And then evolve according to this Hamiltonian. This is the way that you can measure the phase at the end. Why? Well, we can calculate the probability of each outcome. Right? So, well, I have a choice whether to I think this is yeah, for this rotation I can use two convention, right? That the usual convention, I guess, is according, like, consistent with the meaning of rotation with the phase phi here. This give a relative phase of phi to the state 1, right? But if you don't take out the global phase, originally this would give the phase half a phi to the state here, right? And then the other way for state 1, and I think it's easier to calculate this to just use this original thing, which is not the convention. Okay, so well, at this state is just this superposition, right? And then here, at this point, I have this state. And then now I do the Haramat again. Right. I guess I can just write it down. And then I can collect the coefficient and that's a cosine. And if I want a psi here, and well, I hope that's correct. Yeah, of course, right? This is the cosine of phi half, and this is this whole thing, right? And so we get the result that I will at the final measurement I will get the outcome 0 with this probability, right? And the outcome 1 with this probability. And so this is how, in this setup, how you can see the effect of interference. Right? And similar to the double slit, if instead of a, well, or maybe to just elaborate a bit more on this, so here we sort of, it's kind of like a double slit, where in the double slit experiment, the relative phase, so the file here, you can see the result. You can vary the relative phase by looking at like different points on the screen that measure the position of the electron, right? But here there's no screen, there's no continuous variable in the Hilbert space. The continuous variable is just the parameter here that I can vary. So to see sort of the interference fringes here, like you don't really see it, right? You just have to vary this and then just look at like just sweeping the parameters and then see the result. And we can do the same as in the double slit experiment. We can consider another scenario where instead of putting a phase here, I measure here to see if, well, to see if the light beam is, the photon is in this beam, this arm or the other arm, this arm, the other arm, right? Yeah, I realize this box is not exactly the same as this box because this is a weird thing, right? This is not quite the measurement in the circuit diagram, right? Because we are effectively measure in both arms, just to see which arm this is in. But here it's just usually you just put some detector here, right? And then if you don't see the light in this arm, you conclude that the light is in the other arm. So here I do the Hadamard and then I measure in the computational basis to see whether the state is 0 or 1, whether it's in the top arm or the bottom arm. Well, and then you can, oh, okay, I don't have the phase anymore, but well, I can include the phase here if I want. But if I do it like this, well, so after Hadamard, you get the superposition, right? But then after the measurement now, now the state is either 0 or 1. So this will be your row before looking at the result. And well, if you apply the Hadamard gauge, right? Just map 0 state to the uniform superposition, the plus state. Sorry, this has no square root, but this is still the same thing, the same density matrix, right? And in fact, if I put a Z rotation at this point, then yeah, it will not affect this state at all, right? Because essentially this density matrix rho is already the maximally mixed state. So any relative phase that you introduce here will be lost, and the outcome measurement outcome here would just be just 1/2, right? For the result 0 and 1. So a bit of a philosophy time. So new boards would say that the outcome of the experiment, or like whether the quantum system is a particle or a wave, would depend on our whole experimental setup. Right? It's kind of like the system, sort of the I don't know, the actual real nature of the system depends on the way that we measure or interact with it too. And I guess this is sort of the philosophy that Niels Bohr kind of stick with. But then John Wheeler came and then say, well, maybe whether the system maybe the system make a decision to become a wave or particle, but suppose that but we can change the experimental setup like mid-flight, right? Because I can choose to insert either the phase shifter or the measurement here at the last second, or I don't know, last nanosecond or whatever in real experiment. And so this is sort of known as a like delay choice. Experiment or thought experiment. He just play around with the idea, well, if we can do this, if we can decide on our experimental setup as late as possible, well, what does it mean for the reality of the system? But of course, it's just philosophy, right? We don't really have to talk. We don't really need to talk about when the system made a decision to be a particle or wave. Okay, so far so good. This is sort of all set up. Now we can talk about quantum eraser. Let's see. Yeah, I can erase everything. Mm-hmm.
Not here.
To peak. Yeah, well, yes. So I mean, it's just discrete, right? Yeah. Well, so the two peak here, yeah. So there's 2 points, 2 coordinate point, and then the actual, if you don't select for whether you see the zeros, result 0 or 1, the probability is just uniform. But it's uniform in just 2 points. Here too, that I already erased, there's only 2 points, right? But the probabilities will depend continuously on the parameter on the phase phi. Right? One of them is cosine square, another one is sine square. Right. Right. So the yeah. So let's say I include the phase shifter here, right? But changing the phase doesn't change this distribution at all. Yeah. Yeah. Whereas changing the phase here would change the relative height of the two peaks, right? Yeah. So the outcome, the space of outcome is still discrete. There's just 2 points, right? Yeah. But the height the value of each point depends on the phase phi. Yeah, so if phi 0, then you just get a peak here, right? Yeah, and the other way around, which is pi, because I already have over 2 in there, I just get this peak, right? Okay. So now, well, I don't know if I can draw this in the optical diagram. Let's talk about the idea of quantum measurement first. Let's see. And then you ask, well, what the heck are we talking about? Because we already talked about quantum measurement. Yeah, so in reality, the measurement device is also a quantum system, right? So for example, if I have some I don't know, electrons here, and I want to make a measurement, so maybe this go into the measurement device, and then maybe this has the state. Well, I don't know, maybe there's a meter here that say is the spin is up or down, so like it's 0 or 1. So when you make a measurement, well, so what kind of interaction can be a measurement, or a measurement, what kind of system can act as a measurement device? Well, depends on its interaction with the system, right? So, so for example, if I have a state, let's say, let's label this the system S, and then this the meter M. If I want to measure the system in the computational basis, so I would put this state, the system, next to whatever the state of the meter, right? So let's say it's some sort of ready state. So after the interaction, whatever this count as a measurement, the state of the meter should correlate with the state of the system, right? So here I just arbitrarily label the state of the meter here, but the only crucial point is that these two must be orthogonal, right? If we were able to, if we were to distinguish them. Right? And so if I put the state in, if the state of the system is in a superposition, it would create the interaction would necessarily create entanglement, right? SM So in the quantum measurement literature, this would, or quantum foundations philosophy, this would be called the pre-measurement state. And then this process can keep going, right? For example, after the meter, then I can look at where the meter falls, right? Where the meter points to, and then that means that my eye is entangled with the system and the measurement device, and maybe it sort of go into my brain, and then my neuron is entangled with with the whole thing, right? Well, this is sort of sparked like a pretty extensive debate in the quantum foundation, which is that, well, where does the measurement come from, in the sense that in quantum mechanics, we always learn that there are two kinds of evolution, right? One is when we don't look at the system, and then the system evolved by the Schrodinger equation. And the second is when we make a measurement. But what counts as a measurement? This is sort of something that some people want to like define, because there is how to say this, there's no like strict, there's no like physical, well, there's no law written what counts as a measurement and what not. So it's kind of like a Thai bureaucracy, that there's no written rule, and then you can depends on the circumstance, you can do this or do that, and when there's no strict rule, there's a problem, right? Then there's even like some people say, well, what does it mean that when we look at the system, what do we mean when we say, well, if we look at the system, then the system collapse, right? Like, do we does a person that has a PhD, does it have to be a human? That would the quantum state collapse if a dog look at the measurement device and so on? And usually, what in the philosophical jargon, what we do is we have to put something called the Heisenberg cut somewhere, and say that at some point this becomes just a classical distribution, in the sense that well, I can write like this. This is S and M, right? Is that this become a mixed state at some point. And then when we look at it, we see this state with probably alpha square, or that state with probably beta square. But this point is never mentioned, never defined anywhere in quantum mechanics. And so this causes some people like John von Neumann initially to think that to collapse the state, you need consciousness, so that you can put Heisenberg cut here. It's kind of like consciousness is something objective to put the Heisenberg cut. But the now, or I don't know, 40 years ago, we know better. We know a lot better, because we know that the coherence usually happens much faster before anywhere that we want to make want to put the Heisenberg cut. In the sense that when the system interact with an environment, they lose coherence. So going from this to that very quickly. I don't exactly know the time scale, but by our intention and purpose, when you know at this stage where we can look with our naked eye at the screen that shows the result of the measurement, the system has long been decoherent. There's no coherence left between two outcomes that we want to distinguish. Decoherence. Yeah, for example, I can model this process, this pre-measurement, as a C0, right? Because it does exactly that. So I have a qubit here. Let's say the ready state is a 0 state, and then you have the psi here. So what it does here is just copy the information in the computational basis, right? So here. And if we trace out the second qubit, we get this density matrix, right? So it's sort of the key to decoherence. Well, actually, there's a lot more going on in research about decoherence depending on the interaction between the system and the environment, right? The type of interaction Hamiltonian that you put in. But at the simplest level, the main tool of decoherence is that if I look locally at the system, meaning that I trace out every environmental degree of freedom, then I would get a mixture, a probabilistic mixture. But of course, this is I put a question mark here because this is not like a satisfactory solutions to like philosophers or people who really think seriously. Because, for example, in this case, right, so people usually think of this as a transition from quantum to classical, like from quantum amplitude to classical probabilities. But in this case, it's clear, right, that things doesn't become classical just because we focus at one system. You still have entanglement here. It's just that we don't care about the other system that we see. We see the incoherent mixture here. But if we take into account the other system, then of course it's not classical. There's entanglement going on. But yeah, we'll not talk about that point. But yeah, if we want to think about it, you want to think about it more, we want to discuss it, you can talk to me or to each other. But yeah, here is the point here is C0 acts as a kind of measurement device. In the computational basis. Because it records, records the state of, records how much of the original state is in the alpha part and how much is in the beta part. If I want to measure in a different basis, then I would need another interaction that correlate them in that basis. Right? This is just making a correlation in the computational 0-1 basis. And just as an aside, I was careful to mention to say that I copy state in a particular basis, right? Because in general, by linearity, you cannot copy the state in an arbitrary basis. For example, here, so if I want to prove by contradiction, so suppose that I want a unitary that does the following, right? If I have state psi and then I have the ancilla or the meter in some ready state, I want this to be to make a copy. And of course, I can define this in any orthogonal basis that I want, right? For example, we just did this here. But as soon as I apply the same unitary to the superposition, I don't get a copy, right? I get an entangled state instead. So, let's see. So if then by linearity, it's necessary that this is this is the no cloning theorem. So I talk about all that because now I can do okay, I'll use a mixed notation here. Now I can turn the measurement in the Mach-Zehnder interferometer setup to this, right? I can entangle it with a different system. Well, maybe just 0 or something. And then decide to make some measurement, which can be in some basis, in an arbitrary basis that we want to make a measurement in. And this would act as a measurement on the original system too, right? Yeah, clearly this is an abuse of notation, right? Because as I mentioned, this measurement should spread to the other arm too. But yeah, this is meaning that I use C0 to copy the which way information, so information of like which arm the light is on, to this auxiliary system, and then measure it to have the same effect as measuring this system. Okay. Yeah. So actually. It's kind of funny. This is so important that in thought experiment like this, that people usually have a way to call this which way information. And if write somewhere, if you want to sound cool, then you can say it in German too. Called Welcher Whack. Did I write it down somewhere? I'm not sure. Well, I just guess the spelling. Something. Which for us here in the circuit model is really just the information in the computational basis, right? Whether the state is 0 or 1. But now the point here that people who introduce quantum eraser emphasizes is that you can delay this measurement as long as you want. You can already, the lights already go in the measurement out the detector here, and then you can, I don't know, leave the lab, close the lab door, wait 1 year later, and then you decide to make a measurement on this. And now it's the philosophical point that they want to make it, well, now it's sort of like you can retroactively change what the system decide, their decision to be a particle or wave after you already detected them here. Well, I haven't talked about the eraser part yet, why it's called eraser. This is just the delay choice, but it's sort of like an evolution of the Wheeler's delay choice setup. Because now it's not only that I can change the experimental setup mid experiment, I can change the experimental, I can sort of like change something after the measurement is already done. And so what exactly we are doing here? What is an eraser? What are we erasing? So let's draw this as a circuit diagram first. Well, just for fun, I can also put the phase shifter in here. But notice that I can move the phase shifter before or after the C naught. It doesn't matter because it acts in the same basis. It's diagonal in the same Z basis. So I just put the rotation here. And then there's a beam splitter there. Well, maybe I just delay it a bit. And then I can choose to make a measurement here. What is the time? Oh, almost ran out of time. So what is the state here? Oh, we already erased everything. So this superposition, this gives, so yeah, so this is now the state at this point, right? Is this entangled state? If I make a Z measurement here, I would destroy this relative phase, right? And then what goes in the measurement over here would just be a maximally mixed state between the 0 and 1 state. If you measure C, well, I guess I can call it A or call S for system. And so the final measurement here, you have 50-50 probability. However, if I measure x here, so x, and you can do this by doing the harder match first, right? Then make a z measurement. Well, yeah. So what I would apply the harder match, just for the sake of time, let me see if I already calculated somewhere. Yeah, let's do it. So so Hardamat in the second qubit. So let's, I think, collect the 0 and 1 term on the two sides. Yes. Oh, sorry. So we need to do the same thing, minus here. The whole thing is over 1/2. And so now, well, I guess I don't really need to put minus sign here. But now if I measure the second system in the z basis, I pick out one of the term, right? And then, right. So in this case, specifically, you get back the same state. Right? You get back the state not after, let's see. Yeah, you get back the state after the rotation here. So you sort of restore the coherence in the z basis. So just to proportional. So this is a state that have relative phase phi between the 0 and 1, right? And so once you pass this into the Hadamard and make a measurement, you will see interference. We already erased that has, the outcome probability will depend on phi as like cosine square phi over 2 and sine square phi over 2. If I get this state, I can, this is for not to clutter it, let's draw it over here, and then we can stop for today. Which basis? ข้างล่าง yeah.
If we use that basis, we don't see the if you use another basis, you see
In crucially X basis, if you put in superposition on the equatorial plane, right? And then you measure the X basis, you don't get any information about the phase. So in a sense, the X measurement erases the information about the phase from the measurement device. And this is why they call quantum eraser. So let me draw it over here. Yeah. In the sense that the second qubit is storing information about the Z basis of the first qubit. And when the information is stored elsewhere, meaning that the information of the system is correlated to other system, right? That's when we trace out the other system, when we will not will get a mixed state in our system. Or to say another way, we get mixed state because our system is correlated with another system. And then this here, correlated mean entangle. Let's see. Yeah, let's take out the annoying global phase. Oops. Yeah. Well, what is that over there? If I take out this, so and then minus, right? If I just pick out the state where the second qubit is 1, right? 0, 1, and then you have this minus phase. And so what you could do, for example, to restore the first qubit to the same state is that, to the same state as this one, is that if I measure 0, I can apply Z to the first qubit. So I get a classical information, right? Whether it's this term or this term. And when I get 0, I do nothing. I already get the original state that has the relative phase of phi. But if I want to make this state also have the relative phase of phi, then I apply Ctrl Z to get rid of this minus psi. And then if you do this, then in both cases, you'll be able to see the interference here. With probability, cosine square and sine square. Right, because we are doing that so that we sort of that post-processing allows us to sort of ignore this whole thing. Because if you don't have this part at all, then after the rotation, I will get this state, right? or this state after the Z flip. Okay. And then when I do the Hadamard, then I get into the state where I get the amplitude of the 0 state is cosine, and amplitude of the 1 state is sine. Okay, so next time we will talk about why this work and yeah, what's the implication of this. Okay. Question ลืมคืนได้นี่